Hi, welcome back. In this video, we're going to work through two examples of how we find the area between curves with respect to x. For our first example, let's find the area between the curves y equals x squared and y equals 2x on the interval 0 to 2, and that's where that interval is x values. So anytime I'm doing one of these problems, I like to start by graphing it. So I'll graph this by hand, starting with y equals x squared. This is a parabola with the vertex at the origin, and then it opens upward, so it has points at 0, 0, 1, 1, and 2, 4. Then I'll graph the line y equals 2x. So this is a line with a slope of 2 and a vertical intercept of 0, so it passes through the origin and that has a slope of 2. So it's intersecting the parabola at the point 2, 4. Okay, so these are my two curves, and we're going to find this area between 0 and 2 on the x, which is exactly the area where they intersect. So when I'm doing these problems, I like to think of integrating with respect to x as the default, sort of the standard way of doing this, and then we would then try integrating with respect to y with horizontal bars if we needed to, so if we couldn't figure out how to do dx. But let's start with respect to x, and it should work in this case. So here I see that if we have a rectangle that represents our little rectangles that we're going to add up to get the whole area, I can see that the top of the rectangle is the 2x, that's the above function, and the bottom of the rectangle is x squared, that's the below function. And then each of these rectangles has a little width dx. That's an infinitesimal dx, it's just a really, really small width, and we're going to add up sort of an infinite number of these rectangles with that width. So okay, we have our rectangles, and now we just need to set up our integral. So we're integrating on the x from 0 to 2, and then our areas of our rectangles, we take that height, 2x minus x squared, and we multiply by dx. So there we go. As a reminder, this is an integral with respect to x, since the widths of our rectangles are dx, and the bounds are also x values. So we were given x values from 0 to 2 as our interval to work on. You can see that if we were using y values, we could go from 0 to 4, where those intersection points are, but we're going to use x values, that's what we were given, and it is easy because we have y equals for both of our functions, so it was easy to set this up. Nothing went wrong, so let's go ahead and do it with respect to x. Alright, time to evaluate this integral. I'm going to split it up into two integrals just to kind of show those steps. So I'm looking at the integral from 0 to 2 of 2x and the integral from 0 to 2 of x squared. Okay, so for integrating both of these, I'm just using a power rule where I'm going to add 1 to the exponent and divide by that new exponent. So for 2x, I have that 2, it's a constant, that stays. Then I increase the exponent by 1 and divide by that new exponent. So I have 2 times 1/2 x squared, and we're evaluating that from 0 to 2. Then on the next integral, I add 1 to the exponent, so it's 3, and then I will also divide by 3. So I have 1/3 x cubed, again evaluated from 0 to 2. I'll do a little simplifying first, so the 2 and the 1/2 are going to cancel on that first term, so I just have x squared from 0 to 2, and let's go ahead and evaluate these. So I'm going to plug in 2 first, and then subtract off what happens when I plug in 0. So for the first term, I'm getting 2 squared minus 0 squared. Then for the second term, I'm getting 1/3 times 2 cubed minus 1/3 times 0 cubed. Alright, now time to simplify. So I have 4 minus 0, so that's just 4. Then I have 1/3 times 8 minus 0, so that's just 1/3 times 8. To do this by hand, I'm just going to write these both as fractions with 3 as a denominator. So I'm going to rewrite 4 as 12 over 3, and then I subtract 8 over 3, and that's leaving me with 4 over 3 as my final answer. Okay, so 4/3 is our final answer for the area. I like to just finish these problems with a concluding statement. So I'm going to use these 3 dots in a triangle. This is a mathematical symbol that represents therefore. This is my concluding statement, and it says the area between the curves is 4/3. And there we go. That's our first example. Okay, let's do a second example. So let's find the area between the curves y equals x cubed and y equals square root of x. So in this example, we don't have any bounds or interval given, so we need to know what the area looks like in order to set up the integral to solve for it. So I want to show us two different ways to do this. So I always like to graph the functions that I'm given, and I can do this by hand or by using a graphing tool, but it's also nice to know how to do this without graphing, and that's the algebraic method. But I'll start with the geometric interpretation. So if we have these two functions and we think about them on some axes, I know that y equals x cubed looks like this S shape, and then y equals square root of x is sort of just this half part that comes out from the origin. But when I have these two functions, unless I remember really well how they work, I don't really know which function is above or below or where exactly they intersect. I'm pretty sure that the square root of x is above and it intersects the x cubed at some point, but we want to be a little more careful than this, so I want to graph it in sort of a zoomed in sort of way. So let's look at just a portion of this graph. I'll start by graphing x cubed. I know this has a point at 0, 0, and then at 1, 1, and it kind of comes down and up. Whereas if we have the square root of x, this kind of goes above, and it also intersects at 1, 1, and has a point at 0, 0, but the values in between are going above. So you could find this by using a graphing calculator, a graphing tool online, or you can just plug in a point like 1/2 to see what the outputs are. But I'm seeing here, I'm confident with this graph, and now I can tell that the square root of x is above and x cubed is below. So if I look at one of my rectangles, if I use dx, where my height is the above function minus the below function, and the width is dx, my height is then going to be the square root of x minus x cubed. That's the above function minus the below function. Then we also can see our bounds on the graph, so we're starting at x equals 0 and going over to x equals 1. So we could do this with respect to y with horizontal bars, but nothing went wrong so far and this was pretty straightforward, so I'm just going to go ahead with doing with respect to x. Okay, so this is the geometric way, but maybe you're working on this and you're not super sure which function is above or below, or you don't have a graphing calculator and you're just not super confident. You can do some algebra to determine which function is above and which is below, and where they intersect. So the way to determine where the graphs intersect is by setting them equal. So we'll take y equals x cubed and set it equal to y equals square root of x. So we have x cubed equals square root of x. And then we're just going to solve for x to see where these are equal. So I'm going to go ahead and square both sides. That gets rid of the square root. So I have x to the 6th power equals x. Then I just want to solve for x, so I'm going to subtract x over to the left-hand side. I have x to the 6th minus x, and that's equal to 0. Remember, you can't divide by x here because you might be dividing by 0, so we need to just subtract it over and do some different math. And then I'll factor out an x. So I have x times x to the 5th minus 1, and that equals 0. And I can set both terms equal to 0, since if these are multiplied together and equal 0, one of them must be 0. So from the first term, I'm getting x equals 0, and from the second term, I'm getting x to the 5th minus 1 equals 0. I add 1 to the right-hand side, that's x to the 5th equals 1, and then that just is true when x equals 1. So these are now the bounds of my integral, from x equals 0 to x equals 1. These are the places where the curves intersect, and so I know that this is the area I'm looking for. Okay, so this finds you the bounds without graphing. This tells you where the graphs intersect, but you also need to know which function is above and which is below. So the way I like to do this is to choose a value in the interval, so between 0 and 1, choose a value and test it to see which output is larger, so which output would be higher on the graph, so which would be above. So I'm going to pick x equals 1/4 and substitute that in for both of my functions. So I have x cubed, which means I'm looking at 1/4 cubed, and I have square root of x, which means I'm looking at the square root of 1/4. Simplifying these, I'm getting 1 over 64 and 1/2. So 1/64 is certainly smaller than 1/2, and so this tells me that the 1/64 is below the 1/2. That means the x cubed function is below the square root of x function. This aligns with how we drew our graph, but it's just another confirmation that you could be doing this algebraically without graphing if you wanted to. Okay, so from both of these methods, I think we're ready to set up our integral. We have our bounds, and we know which function is above and which is below. So I'm going to put x equals 0 and x equals 1 on my bounds of my integral, and then I do the above function, square root of x, minus the below function, x cubed, and this is with respect to x. Alright, so now I just need to integrate. I'm going to rewrite the square root of x as x to the 1/2, so I'm looking now at the integral of x to the 1/2 minus x cubed. And we use a version of the power rule here, so to find the antiderivative, we're going to add 1 to the exponents and divide by that new exponent. So for the first term, I have 1 over 1/2 plus 1, that's the new exponent, and then I'll have x to the 1/2 plus 1. Then I'll subtract the second term's antiderivative, so that's 1/4 x to the 4th. And we're evaluating this from 0 to 1. Okay, I want to pause here because we now have the antiderivative, and this means we've done sort of all of the new calculus. We've set up the graphs and the algebra to determine which area we're looking for, and we've set up an integral to compute that area. Then after setting up that integral, we found the antiderivative, we solved the integral, and now we're just going to use a fundamental theorem of calculus to substitute in these bounds. So if you want, you could just skip to the end to see the final answer. You could pause and work through this math on your own and see what solution you get, or you could just watch along with me. I just wanted to pause here because it takes me a little bit of time to go through all of the algebra of solving this problem because I'm doing it by hand. So now we're just doing some algebra and substituting in values, which isn't really the calculus part. So you can do what works best for you here. Okay, so back to finishing the problem. Before I substitute in the bounds, I'm going to do some simplifying. So 1/2 plus 1 is 3/2, so I'll rewrite that here. And then, now that I have that, I'm going to just rewrite this complex fraction, the 1 over 3 over 2, as 2/3. So I multiply by the reciprocal, that's 2/3. Then I can also rewrite x to the 3/2 as the square root of x cubed. You can remember x to the 1/2 is the square root of x, so x to the 3/2 is the square root of x cubed. So now I have 2/3 square root of x cubed minus 1/4 x to the 4th, and this is as simplified as I know how to get it before I can substitute in the bounds. So we go ahead and substitute in 1 for x, and then we'll subtract off the result of when we plug in 0 for x. So I have 2/3 times the square root of 1 cubed minus 1/4 times 1 to the 4th. Then I'll subtract 2/3 times the square root of 0 cubed minus 1/4 times 0 to the 4th. And we just need to simplify. Thankfully, these are just 1s and 0s, so it's pretty easy to do this algebra. Okay, so 1 cubed is just 1. The square root of 1 is 1, so I have 2/3 times 1. Then 1 to the 4th is just 1, so I subtract 1/4 times 1. Okay, that's the first half. Then the second half is even easier. Since we have zeros here, anything times 0 is 0, so I'm just looking at 0 minus 0. This second part is going to go away. Okay, so I'm left with 2/3 minus 1/4. Then I just need to put these together in one fraction. Really, at any point here, you probably could have just used a calculator, but I like to go through and do all the steps to show you how you can get the exact answer. So with 2/3 and 1/4, I'm going to get a common denominator of 12. So 2/3, if I multiply the numerator and denominator by 4, I'm getting 8/12. And then I'm going to subtract. Let's multiply both the numerator and the denominator of 1/4 by 3. So I'm going to subtract 3 over 12. Then I'm getting 8 over 12 minus 3 over 12, which is 5 over 12. And this is my final answer. I'll finish it off just by writing another concluding statement. I say, therefore, the area between the curves is 5 over 12. And there we go. Just as a quick comment, every time I get to the end of one of these area problems, I just do a little check to make sure that I'm getting a positive value. So areas should be positive amounts. If you're getting a negative answer, that probably means something went wrong and you should go back and check your work. That's just one thing I can check to give me a little confidence in my answer. Alright, so those were 2 examples of how to find integrals with respect to x. Both of these we actually could have done with respect to y, but I like to start with respect to x, doing dx and vertical bars, and then I only change it up if I really need to. So in the next video, you can see how we use integration with respect to y, and some specific cases where it's really easier to do that. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.